I'm Chris. So actually want to start before I dive into this by asking a few questions because I want to calibrate myself for our audience a little bit and just understand who's here. So everybody know what DNS is? All right. Anybody who doesn't? No one's going to admit it? Okay. All right, good. So everybody knows what DNS is. That was an easy question. So who here is responsible for the DNS setup at the company you work for? Not that many people. Okay, all right, that's good. So I have another calibrating question for everybody. So who knows what a CDN is? All right, everybody knows what a CDN is for the most part, and how many of you use a CDN somehow in your ecosystem or in your, yep, okay, so looks like the same distribution of folks who are managing DNS to a certain extent. And then one other kind of question for everybody here. So who here is focused on the back end or the infrastructure of your application? Raise your hand. A few people, okay. And who's focused on the front end? All right, so a lot of people are focused on a lot of different things, which is good. This talk's going to be relevant for all of you. Some a little more than others. There's some back end in this talk, there's some front end, there's some infrastructure and everything in between. This is about what I expected, by the way. I figured that we were going to have kind of a mixed audience, people responsible for a lot of different things, and so this talk's a little bipolar. We're going to talk about what DNS is, a little bit of remediation on that, how it works, look at how just the performance of DNS lookup can impact a web page load. But then we're going to dig into DNS as a more offensive tool and what we can do with it to make our applications faster. So let me just very, very briefly talk about myself for a second. So as is everybody here, I think I'm kind of a performance geek. I like to make things fast. I come at this from a particular angle, and that is the infrastructure that delivers our applications is what interests me. And for a long time, I've been focused on building infrastructure that enables developers to make their stuff fast. For a long time, I've been doing stuff like early public cloud before Amazon was around and bare metal as a service, built a CDN in the last business I was with. And out of that came some really interesting findings in DNS. DNS turns out to be a really good tool for a fundamental piece of content delivery, which is if you've got a CDN, a bunch of different data centers all over the world, and you're trying to decide which of them should serve up the cat picture to the user right now, DNS is a really good tool for doing that. So in our last business, we built a CDN. We iterated on the technology for making these smart decisions about how to decide which of our infrastructure should serve up the cat picture. And we always wanted to bring that to customers. We never got around to it. The company got acquired, and here we are today. Peeled away from that, started this new company called NS1. Just very briefly about NS1, we're based here in New York. We have offices in San Francisco and Singapore. Been around for about 3 years now. And our focus is intelligent DNS and traffic management for some of the most demanding applications on the internet. There are customers of ours here today, some of whom I can name and some of whom I can't, but some that you probably use every day are guys like Yelp or Imgur. XKCD is a fun customer of ours. Catchpoint, some of you use Catchpoint, MaxCDN if you do content delivery with them, and many, many, many more names. Happy to talk about them sometime and what we're doing with some of those customers. That's us. I'm done talking about myself. So now let's talk about this. I felt like I'm at a web performance group, and if I didn't have a web page test screenshot, I was going to get in trouble. So I put one in here, but this is the only web page test screenshot I have, and all I did here is highlight the domains, and that's what we're going to focus on today. So when you today, and most of you know this, right, load a web page, behind the scenes, there is a lot going on, right? There's a lot of assets in play. There's a lot of different domains in play, and this, I happen to go, and I'll use this as a little bit of an example tonight. I happen to go to the website of a newspaper in upstate New York, which is where I grew up, loaded it and looked at the performance, and I'll admit that I did that because I knew it was going to suck. So this is what I saw when I did that. This is, I'm on request 238 of eventually 400 or 500 that happen behind the scenes for initial page view. So this is what we're dealing with every time we load a web page. And what you'll notice here, I picked a random segment of it, and there's a lot of different domains in play. From, I don't know, markets.finance.something.com, YouTube is in here, some image CDNs, there's the actual web page, fonts.google static, and many, many more domains represented in this single page view, and this is happening all the time when you're using the web or building your applications and embedding a bunch of assets. So that's cool. But why do we care? Doesn't this just work? And why don't we think about it all the time, or why don't we hear about it breaking all the time? Some of us do hear about DNS breaking all the time, especially if we're back-end engineers or site reliability folks. DNS is the bane of our existence on occasion. But most of the time it just works, and it's not something we think about, right? Like we set up our domain and we configure DNS, and then that works, and we move on to the servers and configuring our Rails engine and I don't know what else on the back end, and then we move on to optimizing on the front end and so on. But it turns out that the more you know about how DNS works and the guts of what happens when you have a page load like that, the more informed you are about that, the more power you have to do something about the cases where it doesn't just work, and also the more power you have to use DNS lookup as an offensive tool. So a few topics I'm going to talk about today. I'm going to start super quick, kind of crash course refresher on DNS and how it works end to end. Most of you, that's going to be old news for, but useful to remind ourselves. We're going to talk a little bit about, specifically in the context of a web page load, what can go wrong and how performance can be impacted in those situations. Then we're going to talk about what to do about that, how to make sure that DNS lookup is not causing problems for you, be they always happening problems or intermittent issues that are really hard to track down. And then we're going to get to what I actually get the biggest kick out of, which is how to use DNS as a more offensive tool and actually address some fun new challenges with it. So let's start with a quick recap of what happens at DNS lookup time. How many people here live on a command line? Okay, so we got some command line folks who are going to be okay with this gray right-hand side of the screen, and I'll refer to it. But I'm just on a Linux command line here doing a few things to show in an underlying way what's going on. So a few concepts I wanted to just recap first. The first one is delegation, right? So you own a domain, you go to GoDaddy or somebody and you buy a domain, and that's great, but how do you do anything with it? First thing you got to do is delegate name servers that are authoritative for your domain. You do that at your registrar. You, depending on the registrar, do some config, press a button. The registrar talks to your TLD name server behind the scenes, and here is example.com, which is a real domain reserved for example use cases. And delegated by the registrar, which is IANA, in this case, are two name servers for example.com, A and B .ianaservers.net. So those are the authorities for the example.com domain, and they know everything there is to be known about that domain on the internet. So that's the first concept. Another concept that's really important in the context of DNS is recursive lookup. So most of us know that DNS is a hierarchical distributed database, and that means that there's servers all over the internet that we're maybe interacting with to resolve a name associated with a particular domain. So let's look end to end at what happens when we look up example.com in the notional sense anyway. So very first thing we're going to do is we're going to go talk to what we call the root servers. And the root servers are well-known IP addresses. They're living at well-known IP addresses operated by a variety of different bodies and very redundant, and if these break, the internet is gone, right? So these are the root servers. The way you know about those is they are, in general, hard-coded into your operating system or given to you as a series of what we call hints in your operating system. So that's where we start. And we're going to start there and ask the root servers, hey, do you know anything about .com? And they're going to tell you, well, I don't, but these guys over here do, the TLD servers. So these are the top-level domain servers, and those are authoritative for all of com, and they know everything there is to be known about com and what's under it. So, the next step in a recursive lookup process is we're going to say, hey, com servers, do you know anything about example.com? And I say, no, not really, except I know who the name servers are. The registrar told me that at configuration time, right? So we're going to get back these records A and B.IANA-servers.net, which were configured when we registered the domain. And finally, we're going to go ask them, hey, guys, A.IANA-servers.net, I'm really interested in the IP address of example.com. Do you know that? And in this case, it does. And it's giving back an IP address in what we call an A record, 93.184.216.34. And there's our DNS lookup. And now we can actually go connect to that thing and say, hey, I want the web page for example.com. So that's end-to-end, a recursive DNS lookup. And this is how all DNS works on the internet, this sort of hierarchical infrastructure. There's a lot of other nuance to it, of course. So we can subdelegate domains to other name servers, or we can reference other domains with what we call CNAMEs, and we'll see more of that later. Another important concept, especially when we're talking about performance in DNS, is caching. So any DNS lookup in general is going to be subject to caching. So we just walked through this really long process to find the IP address of example.com, right? If we had to do that every single time, talking to servers all over the world, web pages would be truly slow to load indeed if they have 400 or 500 assets across a bunch of different domains, right? So one of the things that we do is cache at different stages of the lookup process the results of the lookup so that we can reuse them. We, in general, are trying to cache these closer to the user. I'll talk through some of how that happens later. But what I've highlighted here is a cache TTL. And it's kind of a weird number. And the reason is this record was served to me from cache by a caching DNS resolver, in this case 8888, which some of you probably know is Google Public DNS, which is one kind of caching resolver. In general, most of the time, what we see is caching resolvers are assigned by an ISP, and it's not something that end users think about. Probably if you're on Verizon in New York, you're using a caching resolver owned by Verizon and somewhere in the New York region. But sometimes, and increasingly prevalently, users are informed about this stuff, and for one reason or another, be it performance or control, are using what we call public DNS resolvers like Google Public DNS, OpenDNS, there's a few others out there. So those are caching resolvers. By the way, if anybody has any questions as I go through any of this stuff, by all means, just interrupt me. Another kind of caching that happens, and this is in the browser, modern browsers or operating systems or other clients often will do their own caching of particularly important DNS records or high volume, often frequently requested DNS records. So this is just a screenshot from my Chrome browser a couple days ago, and what you see here is a view into the cache of the browser. Most of these things are actually expired, but we've got Google Docs that happen to be there, Salesforce, and got to sell stuff. Optimizely and other kind of behind-the-scenes things are sitting there in the browser's cache, and sometimes we can look in that cache and have an answer before we go out to the internet. So that's a few different kind of players in the DNS lookup ecosystem, and let's look end-to-end at this DNS lookup process. This is really just recapping everything we just talked about. So if I'm a user and I want to go to www.example.com, and I need the A record for that because I got to have an IP address to connect to and request a web page from. First thing I'm going to do is type that into my browser, right? My browser is going to say, hey, do I know the IP address of example.com? And if it doesn't, it's going to go out, it's going to make a DNS query, it's going to ask its resolver. This is something configured at the OS level usually, like Google Public DNS or Verizon's resolver or whatever. Resolver is going to do a little bit of work with its cache, and it's going to say, hey, do I already know the answer for www.example.com? And if not, it's going to say, well, do I know who to ask? And if it doesn't know that, it's going to say, well, do I at least know who to ask about something at a higher level? And if it doesn't know any of that, it's going to go do that whole recursive lookup process we just talked about, starting at the root and continuing to the name servers for example.com and eventually getting back an IP address. It's going to cache all that stuff so it can reuse it again later, return the answer to your browser, and you're going to get a web page. So that's the DNS lookup process end to end. Now, the performance of DNS is a little bit hard to understand, and a lot of this has to do with just the caching that can happen at every stage of this process. We got caching in our browsers, we got caching in the resolver, we got caching of different things at the resolver. And so it's a little bit hard to determine all the time the cause of a performance slowdown from the vantage point of an end user, because there might be caching impacting the performance of DNS at any stage, and sometimes something might not be in the cache and we see slow performance, and other times something is in the cache and we see good performance. So caching really can dominate the performance profile of DNS in some cases, but that said, so caching bypasses most of the lookup process most of the time, but there are a couple of lookups that happen a lot more frequently than others that we need to think about, right? So one of these is that often the browser has no cache or has a very minimal cache. You may have noticed in that screenshot of my browser cache, it had 1,000 entries. And we just saw a web page that was referencing hundreds of different domains. So browser caches tend to be kind of small and not necessarily long-lived. So very frequently, your browser is talking to an upstream resolver, ideally one that's nearby, right, and asking it, do you have information about this domain? And this is just sort of a rule of thumb, and I wouldn't call this based on a bunch of data I just went and crunched the other day, but more on long experience. Probably about 60 to 100% of the DNS lookups done by your browser result in a query out to the resolver. And then the other DNS lookup that happens very often. So queries to the root about .com don't happen that often. We cache for a very long time what the authoritative name servers are for .com, right? And even pretty frequently we're able to cache for a very long time what are the authoritative name servers for example.com, but not nearly as often are we able to cache answers for records under example.com, like what's the IP address of www.example.com, or what's the mail server, or something like that. So those queries happen much more frequently, and I would say anywhere, again, depending on many, many factors, between 5 and 50% of the time when a user says, hey, www.example.com, I want the IP address, that may result in a query all the way through to the authority. There's a lot of things it depends on, including things like the popularity of the domain. So if you're doing a DNS lookup for google.com, chances are it's sitting in a cache somewhere because everybody is looking for google.com, and some other guy probably paid the cache miss penalty a few seconds before you did, right? But if you're looking up some random domain.com that nobody else is using, you're going to have a cache miss happen. So domain popularity is one. Distribution use is another one. So if all your users are using the same DNS resolver, then the chances are, as long as the domain's popular enough, the lookups are sitting in the cache. But if you have a global base of users, there are hundreds of thousands to millions of DNS resolvers out there that they're using, and much higher likelihood that a lookup is not in cache. And of course, TTL, as with CDN and everything else, the TTL of something sitting in the cache can really dominate the cache hit rate. Historically, we've seen, because of this, predilection to have much higher cache TTLs, right? So bump up the cache TTL that'll improve your performance. The penalty you pay for that is you lose a lot of control. When you make a change in your DNS with a very high cache TTL rate, you wait that TTL for that change to take effect. If you need to move traffic over here, or you need to bring a new server online and you're trying to have DNS control your traffic, you can't have a high cache TTL. And we see today in 2016, TTL is dropping like a rock because people are using DNS to control their traffic much more actively. And that causes this lookup and this lookup to happen much more often. So we need to care about. So let's look at a well-managed asset instead. And so I scanned around the page a little more, and here's something that probably is familiar to a lot of this crowd, jQuery. And jQuery operates its own CDN, code.jquery.com, and you can just reference that and embed a JavaScript blob from jQuery and have it pulled into your web page and use it. And a lot of people do that. So it's very important that jQuery manage this asset well and not introduce a lot of overhead. So let's look at what's happening here. So we're going to go through the same process just a little quicker this time. So we're going to figure out who are the authoritative name servers for jQuery.com, and it turns out Cloudflare is. Probably most of you heard of Cloudflare. It's a CDN. They do some DNS too. So that's one set of name servers we're going to have to check out. We're going to follow the chain a little bit more. We're going to ask, hey, do you have Cloudflare, the IP address of code.jQuery.com? And the answer is nope. Just like before, we got a CNAME pointing to some other domain, in this case, netDNAcdn.com. And I'll admit this example is a little more contrived. So this is on MaxCDN. jQuery served off of MaxCDN, which is a customer of ours. So again, we got a bunch of name servers from NS1. So that's the other set of name servers we're going to have to check out for performance. And do we have IP addresses? Yes, we do. So we're done with that DNS lookup process. So we've gathered a couple sets of name servers, Cloudflares and NS1s, and we want to understand the performance of these authorities. And we could plug them into Catchpoint or Pingdom or whatever. Let's just do the same thing we did a second ago. So our Cloudflare or NS1 slow from New York City, and in this case, nope. We're both pretty fast, 1 to 2 milliseconds. So we've got name servers local in New York. That's good. What about California? Same exact thing. And what we're finding here is Cloudflare and NS1, 1 to 2 milliseconds in California too. That's a pretty good sign that we're in good shape with this asset. And we could go take the same measurements from all over the planet and build a latency map of the authoritative DNS servers here. But this is an asset that we're a little less hesitant about than that other wacky ad tech asset that we saw a few minutes ago. So, a takeaway here, if you're trying to build web pages that have a lot of different domains referenced in them that you care about the performance of, is hunt down slow authoritative DNS lookups. They will not hurt you every single time because of caching, unless there's a random host name. But you will see intermittent slowness because of these. Some percentage of the time gave you some indication of what those percentages might be. And it's hard to track that stuff down because of the impact of caching. So that's one takeaway. What's interesting here is a lot of us operate our own domains, and we want to make DNS lookups for our domains fast, not just embed assets that are from a fast bunch of domains, right? So how do we do this? A few things that we have taken over the years as common knowledge about DNS are really getting a little stale. And so let's refute a few of the basics of what people tend to do first. So one is it's never okay for one of your authoritative name servers to fail. And historically, this has not really been the case. DNS is built to be resilient, and the reason that you assign multiple name servers to your domain is so that if one of them fails, there's another one that you can go talk to, right? But how does that actually behave in practice? If NS1 example.com is having a bad day, and pretend there's a resolver in here somewhere and we're following the full DNS lookup process, we're going to do the lookup. We're going to send a UDP packet to ns1.example.com. We're going to wait a little while because UDP is a connectionless protocol, and the only way we know whether we're going to get an answer back is waiting a while and then giving up eventually, right? So usually that timeout you'll see is about 1,500 milliseconds. One down name server can result in a 1,500 millisecond delay in this end-to-end DNS resolution process. Not okay for one of the name servers in your loop to fail, even though DNS is built to be resilient in this way. It was never considered as a performance tool, right? So it's one thing to think about. Another one is geographically redundant name servers. So it turns out that the way Cloudflare is fast or the way NS1 is fast in California and New York has nothing to do with the fact that we have different name servers in different regions. And we'll talk about what we actually do in a second. But this is something that's been done historically, right? So we've got a name server on the East Coast of the US, and in case there's a cataclysm of some kind, right? We want to make sure our other name server is somewhere else, so that when that lookup fails to the busted NS1, we can fall over to NS2 in some other locality. This is your typical kind of disaster recovery setup, right? The way we did this historically was with slaving. We would run a name server over here, we'd run a different one over here, and we'd slave all of its data from the first one. And that's great, and that is indeed resilient. And In fact, one of the things that we do see out there that helps us on the performance side in this kind of a setup is DNS resolvers like Bind or Power DNS or some of the others that are out there have built in an idea called smooth round trip time, where I tend to think of it or talk about it as performance affinity. They remember which of the name servers for a domain was fastest for them recently, right? And so they will preference that. So this guy over here will remember most of the time when I do a lookup, NS1 is faster than NS2, and so I'm going to send most of my lookups to NS1, but occasionally I'll send one to NS2 and see if it got faster somehow. And that's great, but most resolvers, well, okay, a small majority of resolvers actually do this today, and all the rest do not, and they'll round robin the traffic across your name servers. So if you've got one on California and one on the East Coast, for those users using those resolvers, which you cannot control that they're using those resolvers, right, you're paying a performance penalty. So the other point here is even when this is in place, do you really want to leave control of your performance to the clients, in this case the ISPs and their resolvers, and are they going to manage that well over time? I don't think so, but your decision. So geographically redundant name server is not quite the answer. How many folks here use managed DNS network as part of their, anybody here would like an explanation of what managed DNS is? Okay, all right. So managed DNS, very simple idea. Let somebody else operate your authoritative DNS. The reason you might do that is this stuff gets kind of complicated, and we'll talk about even more complication over time. And you don't want to worry about the reliability or the performance or the other characteristics of your authoritative DNS. You want to let somebody else worry about it so you can solve the problems you are actually out there to solve. So one of the ideas that's kind of crept up over the last 7, 8 years as managed DNS has become much more prevalent is if I want to solve these problems, I want to have fast DNS. I don't want there to be failures of my name servers. Need this notion of redundancy, but also high performance globally. I should just use a managed DNS network. And we'll talk in just a second about how these things get built. What's interesting about this data is it shows that not all managed DNS networks are created equal. In particular, one of the ways that most people have historically kind of measured the likely performance anyway of a managed DNS network is how many facilities does the network have globally? You might look at a map and you might see that particular managed DNS provider operates 40 different DNS facilities around the world. And you might think, wow, they must be pretty fast compared to this guy who operates 15 down at the bottom. But what this data actually shows, so this is global performance data right out of Catchpoint from all 400 odd something of their nodes of a bunch of major managed DNS providers. And on the right is the number of facilities they have, and on the left you see the average global response time of these networks in milliseconds, and lower is of course better. And what we found over time is there's a little bit of a sweet spot here, somewhere between like 15 and 30 different nodes globally in a particular configuration we'll talk about in a second. And as you get beyond that, there's really no guarantee that's going to improve your performance. In fact, often more facilities globally is correlated with lower performance, and that has a little bit to do with how the traffic is managed. So finally, let me just talk about how this actually happens in practice today. Who here knows what anycasting is? 1, 2, 3, 4, 5. Okay, good. A few people know what anycasting is. So now we're getting way down into the guts of the internet, right? So anycasting is the idea that an IP address can be announced from more than one place or more than one network. So what you see here is a bunch of different servers all around the world that are all ns1.example.com, all have the same IP address. And how does that work? We're down in the guts of BGP, which is the protocol routers used to talk to each other. And if you have a router here and you have a router over here, and both of them say, hey, next hop, I know how to get to 1.2.3.4 or whatever the IP address is of ns1.example.com, then the next hop router can make a decision. It says, oh, there's a path over here to this guy who says he knows how to get to ns1.example.com, or there's a path over here to this other guy that is much, much shorter. And I'm going to pick always the shortest path, right? So this is kind of a notion of topological distance on the internet. And this is how modern DNS platforms work. They anycast the IP addresses of their name servers, This is how, if I felt like it, I'd zoom all the way back to those trace routes that we saw to Cloudflare to NS1, and it's how we get for the exact same IP address, the same roughly local response time in New York, in California, in Singapore, in Australia, like wherever in the world, is we actually do put servers in all those different markets, and then we anycast the IP addresses. So anytime you try and reach that IP address, you're routed by the BGP protocol, the underlying kind of protocol of routing on the internet, to the topologically closest server. So anycasting, I'm not going to talk in any more technical depth about it. Grab me afterward if you want to. Suffice to say, it's expensive, it's complex, you have to build your own network, you have to own your own IP address space, your own AS number, you need to operate routers all over the world, you need to have connectivity to good, consistent set of tier 1 providers all over the world, and you really should not do this yourself, trust me, it sucks. So don't build your own anycasted DNS network. This is why people use managed DNS today. They start to care about DNS at this level. They care about the performance profile of anycasted or of authoritative DNS, and this is how you eke this performance out on a global basis, not just on a local basis. Last thing I wanted to do, and then I'll switch to a different topic, is look at a well-managed property. So I loaded the New York Times, canonically pretty fast page view for me, and I was just kind of curious who actually does the authoritative DNS for every single domain that is referenced on the front page of NewYorkTimes.com. And it's a little bit more condensed than the Watertown Daily Times upstate. They have a much tighter web page, but they still had, I'll show it here, but something like 150, 160 different domains referenced at page lookup time. So here's just a little shell. And what I did is I grabbed a HAR file from Web Page Test, which is just the archive of all the assets that loaded when we went to NewYorkTimes.com, and then I parsed out all the different URLs and all the different domains. Then I did a few DNS lookups here to say, to follow those CNAME chains that we talked about earlier and extract all the eventual name servers that we would be talking to behind the scenes if we wanted to fully load this thing, and then I listed them all. So those are all the different name servers referenced by domains, or used by, sorry, domains for authoritative DNS on the front page of New York Times. And let me just categorize these for you a little bit. So 100% of them are serviced by anycasted managed DNS networks or anycasted CDN DNS networks. And just a quick note there. So CDNs, most of you are familiar with CDN, operate their own DNS networks pretty often so that they have tight control over how their DNS responds and routes users to the cat pictures like we talked about earlier. What we're seeing here is really two classes of domains that are serviced by CDNs, content delivery networks, like Facebook's or Google's, who are serving their own content from their CDNs that they've built out. These guys have lots of resources and run this stuff on their own. And then you've got the CDNs that people are renting, like Akamai or CD Networks or Edgecast, that you might put your own content on to serve quickly. Those are the CDNs, and on the managed DNS side, we're in there somewhere, probably some of the ad tech domains we work with. Amazon runs a managed DNS network called Route 53, Dyn, Akamai, and that is the sum total set of name servers that you're interacting with to load all of the assets on NewYorkTimes.com. And I happen to know that most of these or all of these are anycasted and very fast, and that is one of many reasons I think that the NewYorkTimes.com loads pretty quickly, not just here in New York, but all over the place. So that's a well-managed property. And now, I mentioned at the beginning I was going to be a little bipolar. So we've dug into the performance profile of DNS lookup, but let's talk about what more we can do in context of DNS and how we can go on what I call offense and use DNS to improve the overall performance of our application. So very first indicator we ever have, right, that somebody might be interested in interacting with the infrastructure behind an application is that they type the URL of the application into the browser and they press enter. Like, that's the very first indication we have. Until then, we have no signal that says this user's probably going to want to use Yelp. It turns out this is a very important step in the application delivery process. There's a lot that we can do in context of this step to optimize the future delivery that is done by the application over the course of the session that user has. One of the most important things and what I'll focus on is what we call service endpoint selection, right? So this is the idea that if, I'll use Yelp.com as an example, if Yelp.com is serviced out of multiple data centers, maybe they're in a bunch of different AWS availability zones, or maybe they're using a few different CDNs, or maybe their infrastructure is elastic and they're scaling up and down with demand. In all these cases, we have a service endpoint selection problem. Which data center should serve the cat picture to the user right now, or which CDN, or which newly scaled up elastic load balancer, or whatever it is that we're using, should the user interact with to receive service from this application. So I think I have a few more kind of questions I want to ask everybody, just to, not so much to take temperature, but to see how people are thinking about this stuff. So first question, how many people here operate applications out of a single data center? How many people have a DR site? So, you know, the East Coast explodes. You got something in California. Okay, good. How many people are delivering an application or a website or content or something like that out of multiple data centers in an active-active configuration? Okay, so a bunch. Okay, good. How many people using more than one CDN? Here's another one that's interesting. How many people have audiences that are primarily local, like in a particular city or particular region? Okay, a couple. And then how about audiences that are not like hyper-local, but maybe like USA only or Europe only? Okay, not. Okay. All right. And then how many people here have a global audience? Who cares about users in Singapore as much as you care about users in Amsterdam? A few. Okay. So you guys are the future. Increasingly, what we see at the upper end of the internet, almost every one of our customers has a global audience. Right? They care about users in Singapore. They care about users in Europe. They care about users in South America, Australia, not so much Antarctica, but maybe eventually, who knows. And they're operating infrastructures that are very, very distributed, right? So multiple CDNs in play because CDNs are starting to specialize and be good at particular things or good in particular markets. Multiple data centers that are active all the time because it turns out pushing a big red button and failing over to a DR site is maybe not the actual best DR strategy and the fastest to take effect. And also because your application is probably pretty dynamic and all the delivery that you're doing can't happen through a CDN, which is better at serving up static content, right? So all these reasons are why we're seeing a pretty broad shift in how people build and deploy the infrastructure for their application. So let me just walk through this very briefly. So not very long ago, like 13, 14 years ago, and probably for many people still today, this is what your application infrastructure and maybe your users look like. Pretty localized set of users, and you put your infrastructure near your users, and probably you got a data center, and it's probably got a load balancer and some, you know, application servers or web servers or whatever in a database behind the scenes. And this is what web applications have been for a long time. What we started to see, actually more like 9, 10 years ago, much more of, is we were trying to improve performance for a more distributed set of users, right? So we might have the same core infrastructure in what we call an origin now, like your core application infrastructure, load balancer, web heads, database, maybe a little bigger. But we started to see the use of CDNs more and more and more. Now everybody knows what a CDN is, and everybody's using a CDN. And the reason is you're serving up cached static content to users who are all over the place, images, videos, JavaScript blobs, whatever, caring about that audience, trying to improve performance for them. And here is what we are seeing, honestly, for us, with many, many of our customers, most of our customers today. And, you know, I might flatter myself by saying that our customers tend to be kind of leading indicators of what's happening, but I do think that that's true. So the biggest properties on the internet today, this is what it's starting to look like, right? We're no longer in a single origin facility. We're servicing in an active everywhere kind of sense. out of a bunch of different distributed facilities with master replication going on in the database. We've got more than one CDN because some CDNs are good in Europe and others are good in South America and others are better in Asia. A lot of reasons why this kind of trend is happening. We talked about some of them already, but we're moving the application to where the users are. Users are impatient. It turns out that guys like Facebook and Twitter and Google, you can blame them for this. They paved the way here, and now we all have to catch up, right? So users in Singapore got used to being able to go on Twitter and tweet, or go on Facebook and see what their friends are doing, or go on Google and get a result very, very quickly. And when some other web application is vying for a user's attention and is not performing that way, and it's no excuse where the user is in the world, they're going to lose interest and move on to the one that does, right? So CDNs can't solve this problem on their own because CDNs are inherently pretty static in the way they think about serving up content. They serve up pictures and JavaScript blobs and CSS and video and that kind of thing. But if you have a user interacting with an application, let's use Yelp as an example. Again, a user wants to go to a restaurant in Hong Kong, right? They need to do a database query. They're going to do something that is specific to them, get back some results, want to interact with it somehow. And the application infrastructure, the database itself, the application servers, load balancers in front of those need to be near the user to provide the kind of performance that those users have come to expect. So that is some motivation for the way these infrastructures are being built to service applications and websites and so on for a more modern audience and with a modern set of infrastructure. So what's DNS got to do with this? Turns out that DNS lookup is a really good time to do this endpoint selection. It is, like I said, the first indicator we have that a user is interested in interacting with the infrastructure behind an application going forward. And it's a good time for us to choose which of that infrastructure should they call out to and work with. Another reason is that DNS lookup is pervasive. It's there. It's been around since 1983-ish. And everybody is using DNS, whether they're thinking about it or not, right? When they enter a domain name, or even behind the scenes when you talk to api.whatever.com out of your mobile client, there is a DNS lookup in that process. Another reason is really very lightweight, right? So because everybody's using DNS, making changes to DNS is a very easy thing to do. It's configuration change, right? It is not, let's add a new hardware load balancer over here or add some GTM appliance over here. DNS lookup is a lot easier than that. So these are some of the reasons why DNS lookup has proven to be a pretty good time to do what we call service endpoint selection. So let me see, we're how far in here? Getting close, almost done. So we're going to talk about a very quick example here, endpoint selection example, and we're going to use an API as the example, in this case api.example.com. And suppose we've actually got active everywhere infrastructure in a few different markets, right? So West Coast of the US, East Coast of the US, Europe, maybe Latin America, that's where we have users we care about. And we want users to be serviced by the API endpoint that is going to be most performant for them. Historically, the way we would have done this is what we call geographic routing. Just to explain this verbally, because I don't know how to make diagrams for all this stuff. Geographic routing is the idea that at DNS lookup time, we're going to try and guess at where the user is, maybe based on like the GeoIP data of their DNS resolver's IP address or something like that. We're going to try and send them to one of the service endpoints, one of the API hosts that is near them. And the assumption there is that proximity has something to do with performance, and often it does, but not always. And I just want to just quickly give everyone a view into where this is trending, what we're seeing today, and not delve too much more into it than that. So it turns out there's a lot of other information we may want to act on to make a decision at DNS lookup time of which API endpoint we're going to send a user to, right? So one kind of information like that is what we call infrastructure telemetry. We want to know in your infrastructure, on your API servers, what is happening right now. We want to know things like the topology of your network. Has new infrastructure spun up? Do you have a new API server in Singapore now all of a sudden, or not? I don't know the health of your systems. Either is it up or down right now, or something a little bit more nuanced, like maybe are these servers approaching some kind of a load threshold beyond which we know they're going to fall over? Or are they well beyond that and we should not send any new traffic there, or something like that? Even things like, this is maybe a little less about performance, but about dollars. Have you hit your bandwidth commit yet this month on this particular CDN, or something like that? These are the kinds of information we might want to act on. The other kind of information, which is especially important with respect to performance, is what I usually call network telemetry. So this is, we want to know what's going on between your users and your infrastructure right now. So for example, my phone is on Verizon in New York, and I want to know in the last 5 seconds, what is the response time for a user on Verizon in New York to a web server in AWS EC2 East? And if I know that, that's really interesting information for making a routing selection or making a decision about which of your infrastructure in EC2 East or West or Latin America or Singapore or whatever should service this user right now. Just kind of tying this all together, what we're seeing in our platform and a few other modern DNS platforms is this tendency toward what I'd call data-driven DNS traffic management. This is sucking on all this data, like the infrastructure telemetry, the network telemetry, in real time, and driving decisions with it, so that when we get, call him Bob down here, says, I want the IP address of api.example.com, we maybe run him through a little bit of a modeling process to try and understand who is this guy, what network is he on, how's he connected to the internet, is he on a mobile device or not, certainly where is he geographically, and so on. And then we compare that with everything we know about your infrastructure, about what's going on the internet right now. We make a decision that has nothing to do with simple geography, but has to do with the actual metric of performance that you're trying to optimize. And often what we find is that this is done in a very application-specific way. You may have a particular strategy you want to enact, or a particular metric you care the most about that you want to optimize. Maybe it's not response time, maybe it's throughput because you're serving up video or something like that, or packet loss because you're sending users to game servers. And then we make a selection based on all that data that is very specific to that user and the network they're on. So I've talked very fast for a while, and I'm just going to wrap it up a little bit now with a quick recap of the two major topics that we talked about, right? So first one is on the DNS lookup performance side, right? We looked at what happens especially in authoritative DNS lookup, because that's what we have control over, when there's a slow authority in the mix and there's a cache miss, and what we can do about that. And one very clear takeaway is be ruthless with this. Go look at the performance of DNS lookup for all the assets embedded on your page and do something about it if you see slow DNS lookups, because they can block page loads. And then the second topic we talked about a little bit more briefly is investigate. If you're ready for it, if you're using multiple CDNs or multiple data centers, or you're thinking about doing these things, investigate DNS as an option for controlling this traffic based on data that informs the DNS, which of your endpoints, your data centers, your CDNs, et cetera, are going to perform well for this user right now. So with that, I'm all done. The other thing I forgot to mention, I didn't raise my hand earlier when Dimitri asked who's hiring, we're hiring. But not so much on the web performance side, more on the side of building tools for developers to enable web performance. So if you want to talk about that, come find me. And with that, I'm all done and happy to talk. Yeah, there's a lot there. So you know what I'll do? Go ahead. Yeah, I'll repeat that. So the question was, I gave a bunch of examples of kind of telemetry that we either gather that customers are sending to us and that we're making routing decisions based on, and can I give some examples of that, right? So what I'll do is talk through my favorite example, which is the very first customer we ever had about 3-something years ago, company called Integral Ad Science, which is, it used to be a block from here, and now they're a few blocks from here. They're an ad tech company. And let me talk about this at a pretty high level about their problem, and then like the solution that is still in play today. So let's first talk about their infrastructure. So they operate infrastructure in 4 regions globally, East Coast of the US, West Coast of the US, Asia Pac, and Europe. They have users who they need to show ads to in all those markets. And in each of those markets, they have 2 kinds of infrastructure. One is co-located infrastructure, so physically deployed servers that they have purchased and own, and AWS infrastructure, so they're renting infrastructure from Amazon. And there's some characteristics of those 2 different kinds of infrastructure that are important. So the co-located infrastructure is very economical, right? But not very elastic. But AWS, at their scale, not economical at all, super elastic. So you maybe see where this is starting to head. The problem they had is which of their facilities should service this particular user right now. And the way we solve this is, and where the telemetry comes in, I think will become apparent as we talk through this, get a DNS lookup for ads.integral.com or something like that. Which of their infrastructure should we send the user to? First thing we're going to do is look at some basic health information. Is this facility up or down right now on kind of a global basis? So that's here, maybe we're pinging it, or maybe they're sending us data from Pingdom or Catchpoint or something like that to inform that decision. But assume it's all up for now. Then next we got to decide which region should service this user. Historically, we might have done that with geography. Today, maybe with performance telemetry, right? So we're measuring from all the different regions with respect to all the different ISPs and saying, look, it's users on Verizon in New York, and we know that the performance of users on Verizon in New York to their East Coast facilities is best right now. So we're going to pick the East Coast region. And now we've selected a region. Which data center should service the user within the East Coast region? It's either going to be their big co-located facility, which is cheap and inelastic, but or it's going to be the AWS facility, which is expensive and elastic. So nominally, most of the time, they want to use the cheap and inelastic facility that send like 98% of their traffic there, and then maybe a little bit to Amazon because they want to keep the application caches warm. So we're sending a small percentage there. And then the next decision is, well, we actually want to make sure we send the same 2 or 3% of users to Amazon because we care about data cache locality. So we're doing some notion of stickiness here. And the final thing is maybe one of their customers who knows who comes along and says, I have $1 million and I want to buy a lot of ads in the next 10 minutes. And so they do that. They say, fine. And they start serving up more and more ads and traffic spikes. And we're getting load telemetry off of their load balancers, which are telling us, hey, here's how many connections are active on this load balancer right now. And we see that start to spike. They've told us, hey, here's kind of a low watermark after which we start to get a little uneasy, and here's a high watermark after which we fall over. Make sure we never hit that once we start to hit this. And we do what we call load shedding. So we're getting this telemetry off of their load balancers. We see that we start to cross that low watermark, and we shift traffic in proportion over to Amazon, auto scale up, absorb the spike. As it dissipates, we shift back. And so, in that specific situation, we talked about health or reachability a little bit, right? We talked about load data. We talked about, in their case, latency data, and maybe a few other things that we're acting on. So that's a simple example. Yeah. So the question was, how much of a performance hit is there to, how much of a penalty do we incur to inject this kind of intelligence? And the answer is we don't. The DNS lookup is going to happen anyway. What we're doing is, not for all of those different things I talked about, interacting on the network behind the scenes. Those decisions are all made based on data that's been shipped into the system in a little DNS kernel that is executing every time there's a DNS lookup. So, the lookups I showed earlier, let's just zoom way, way back to here. The lookups we showed for whatever that domain was, Perso or the weird ad tech domain, we're doing this kind of stuff in a millisecond or something. Yeah, average TTLs we're recommending. This is a fascinating question, and the real answer is it depends, of course. But You know, when you're doing all this wacky stuff that we're doing in this day and age and do all this kind of service endpoint selection, you need a low TTL so that you can control your traffic at fairly high frequency, right? And the challenge of that is there's a performance impact every time there's a cache miss, which is why this stuff is important. So these two areas are tied together. There's a few other things I think it's important to say about that. So historically, by historical I mean like 5-6 years ago, I would have recommended where possible higher TTLs than I would today. I probably would have recommended 5-minute TTLs or 10-minute TTLs, even for more dynamic records. Today, it's coming down. Our customers want to control things at much higher velocity. And you know, there's another factor here, which is what is the lowest TTL that a DNS resolver will respect? For a long time, historically, and still today, we run into DNS resolvers out there on the internet. Who knows who's operating them, Comcast or somebody, that do not respect the TTLs you give them. So you tell them, hey, you can cache this for 60 seconds, and they'll cache it for 3 days, right? And that's bad, but that's happening much, much less than it did in the past, and so you can actually expect these low TTLs to be respected at a very high rate. So the question was, how do you, actually, let me restate that and you tell me if I'm getting it right. So you asked, how do we keep the integrity of geolocation data when what? Sorry again? So the important question here is with respect to whom, right? And so, you know, when we give a different response, you know, maybe based on geography, for example, right? That response is given to a DNS resolver, and that DNS resolver, in general, is relatively local to the users who are using it. And in fact, we have a lot of data about this. So most of the time, DNS resolvers are geographically very close to the users who are using them. There's an exception, which is Google Public DNS or Open DNS. If you're using Google DNS here, you're probably using a DNS resolver in like North Carolina or something, right? So if I have a more nuanced decision to make geographically than East Coast or West Coast, if I want to make sure you're sent to the New York server and somebody in North Carolina is sent to the Georgia server, that gets a little harder if you're using a DNS resolver that is distant from you. However, there's good news, which is the DNS protocol has changed in the last 4 or 5 years now, 5 years. There's an extension added, and it was for this exact reason. The extension is called eDNS Client Subnet, and what it means is Google Public DNS, Open DNS, number of other DNS resolvers now will actually forward us, the authority, information about the IP address of who is asking the question, and then they will only cache the response with respect to that set of end users. So I would get from Google Public DNS, if you did a query today, /24, if that means anything to anybody, a small block of IP addresses, which I should make my routing decision with respect to, and then they will cache the answer only for that set of users. If somebody comes from a different ISP, they'll send me a new query and get a different answer. So that's some good news, and specifically applies in this case where we see users using fairly distant DNS results. How do you test the lookup latency in different places in the world? So this is a very coarse approach, right? We just trace routed from a few servers we have. I have a very simple recommendation, and a little bit of an expensive one, but if you have a budget, use Catchpoint. And so there are a few other companies out there I would recommend like this. You can go Google for Catchpoint competitors if you want other examples. Catchpoint happens to be who we use. So what these guys operate is a network of 400-something odd nodes around the planet connected to different ISPs, and you can go ask their network, what's the performance, what's the round trip time from your node on China Unicom in Shanghai to this particular IP address. And of course, you can do much, much more than that, but that's the simple answer I would give. And that's really the right answer, is get a lot of vantage points and look from those different vantage points. Now, there's also some other things you can do on the RUM side and so on, but parsing out what is a problem with the user's interaction with their DNS resolver and what is a problem with the authoritative DNS setup for this domain is a little hard in that case. Don't embed third-party content that has crappy DNS, and then they'll fix it. But that's the simple answer, right? There's really nothing you can do because you do not control the domain used by these third parties, other than be aware that it is happening and make a choice about which domains to let into your web pages. And you saw this with New York Times. If we go look at these guys, again, they made a very concerted choice to make sure that nothing that isn't serviced by a well-managed authority is on. That's a really great question, and I don't know the answer to that. I think that's a great question. I wish I knew. So a little context on NS1. I may have mentioned this earlier. We're not an old company. We're not exactly new to this stuff either. So we went through a very quick ramp when we got started to get up to what I'd call very competitive performance, top 1 or 2 DNS networks on the planet in terms of rough response time, right? And then it gets a little more tactical after that, right? Like, what are the markets? That's what we focus on now. We don't focus on some aggregate global performance, but what are the markets where we could potentially do better? How do we do that? That's one strategy. Now, there's another thing that's worth mentioning, which is there are very difficult markets on the internet that need different strategies, and I'm thinking China here, where it's not sufficient to just add more nodes to our globally anycasted network. It involves deep relationships with carriers and providers in those markets and understanding how connectivity works. If you have a .com domain, you will never service it effectively off of name servers in mainland China. You need a .cn domain for that, thanks to the Great Firewall and lots of other challenges. But yeah, that's my simple answer is I don't think anybody's done with this stuff. We're all optimizing, and it's a race to the bottom in terms of latency. But we're also never going to have a server. There's a speed of light constraint, right? We're never going to have a server in every room. So there is a lower bound.